So this lecture is all about z-scores, and now we're beginning to come to the end of descriptive statistics and move into inferential statistics. So in other words, instead of just summarizing, organizing, and simplifying data, we're going to begin to learn how to take data collected from a sample and use the results from statistical analysis on that data to make informed conclusions about the population. So this lecture will cover the characteristics of the distribution, which is related to three topics that have already been covered this semester: shape, central tendency, and variability. Then I'll move on to how you can identify extreme scores based on the mean and the standard deviation. So if you remember from variability, it's not just, oh, my score is above or below the mean, but how far above or below the mean is it in terms of how far above or below the mean most scores are in the distribution. Then I will talk about the information that's provided by the z-score. The number that you get for a z-score that you calculate tells you two different very important pieces of information. Then I'll move on to the formula for a z-score in both the conceptual and mathematical form. And then we will do some calculations. So finding z-scores for specific x values, and then reversing that formula to find specific x values based on the z-score. And then how to use those formulas to standardize distributions and to look at converting x values into new x values for new distributions. And then quickly look ahead to inferential statistics and how z-scores can be used to make data-driven decisions about populations. So there are three major characteristics of the distribution. Shape is, remember when we looked at frequency distribution tables and graphs where we tabulated the number of individuals with each response for x and then used those to create bar charts and histograms to look at the shape. And the major shapes of the distribution are normal and skewed. Now, the skewed distribution, positive or negative skew, those are really important when we were just talking about descriptive statistics, but for our purposes in this class, when we move on to inferential statistics, the only shape that we are going to be concerned with is the normal distribution. Then central tendency was what we talked about in chapter 3, and central tendency is just trying to find a number or a couple of numbers that represent the most typical score for the entire distribution. Just a number that accurately represents the trends in the data. And remember, central tendency was all about the mean, the median, and the mode. Well, just like the only shape that we are really going to be concerned with for the rest of the semester is the normal distribution, the only measure of central tendency that we are going to be concerned with is the mean. And that's because it is the point of reference for variability. And variability is the third characteristic of distributions. So variability is just a fancy word for the differences among the scores. So are the scores the same? If so, then there would be no variability. Are they all clustered around the same score or clustered around the mean or similar? Means there's going to be low variability. Or are scores really spread out across the entire range of scores? Then that would be high variability. Less consistent, more variability. So I talked about two major types of measures for variability. One is the range, which is just really the number of response categories. And remember, there's two different ways to find the range depending on if you have a discrete or continuous variable. But the most important measure of variability that we're going to be talking about in this lecture and for the rest of the semester is the standard deviation. And that's just a measure that tells you the typical distance of all scores from the mean of all of those scores. And the z-score is very closely tied to the mean and the standard deviation. So the first thing, how do scores compare to the sample or population that they come from? So before we cover inferential statistics, it's important to understand how individuals are related to the samples or the populations they're drawn from, and then eventually we'll get to how samples are related to populations and other samples. So when you want to understand how individuals are related to their population, for instance, to find out how well you performed on a quiz relative to the rest of the class, then you need two pieces of information. You need the mean, which tells you the direction of the difference. So is your score below or above the mean? And if the mean is low, then it's probably easier to feel really good about your quiz score, whatever it is. The standard deviation, so that tells you about the distance. So am I slightly or extremely above or below the mean? So you can't determine are you extremely or slightly above or below the mean just by looking at how many points away your score is from the mean in terms of raw scores. You need to consider the standard deviation so that you have a measure of the relative magnitude of that difference. Because you need to know how spread out scores are. If most people scored around the mean, so scores are consistent, then you'll have a small standard deviation, and any small discrepancy from the mean would be considered extreme, because most scores fall around the mean. So if you don't, then you're probably a more extreme score. But if there's people scoring all over the place, then you're going to have a large standard deviation, and you'll require a larger discrepancy from your score from the mean to be considered extreme, because there's tons of people in the sample or the population that don't have scores that are close to the mean. So here's a picture of that phenomenon, looking at two different distributions. So this first distribution, the blue one, this would be a lower variability distribution. It has a smaller standard deviation than this distribution, which is a larger variability distribution, higher standard deviation. And the reason that this has less variability is because most of the scores, vast majority of scores, are clustered right around the midpoint, right around 70. There's a lot of common scores in this data set, and then there's, some extremes on the high and the low end of the distribution. And just as a reminder, remember, the y-axis is all about the frequency, and then the x-axis just tells you the different values in your data set. So if you're at a value in your data set that corresponds to a high frequency part of the distribution, then most of your data points are right at that value. Or in other words, most people have a quiz score right in here at 70. Now the yellow distribution, the larger variability distribution, represents more spread in scores. So there's several people with 60, 70, and 80, not just clustered around 70, and then there's a few more with some of the other scores in the data set as well. So there's a lot more differences among the scores here, whereas in the blue distribution, almost everybody got a 70% on the quiz. So back to considering not only the mean but the standard deviation when you're trying to see how extreme your score would be in this example. The mean for both of these distributions is 70. So if you got a score of 80, then you could say, in this distribution, well, you're still part of a relatively high frequency part of the distribution in this distribution. So you draw a little arrow up, you say, oh, well, I'm not really that extreme. I'm not in a tail of the distribution at all. I'm right around where most other people fall. Yeah, my score is above the mean, but it's not extreme. But if, for example, you get this score within a lower variability distribution where most scores are clustered around 70, then you're a little bit more special. You're in a lower frequency part of the distribution compared to this one, and you're a little bit more extreme than what you would have been in the other distribution here. So it's important to consider how spread out scores are from the mean when you want to compare any single score to the mean of the distribution to find out where you fall relative to the rest of the people in that distribution. So the z-score is a really nice measure that quantifies the relationship between raw scores and the mean in terms of standard deviations. So the z-score just provides a shortcut for you to see how extreme any given score is relative to the rest of the distribution of scores. So the first piece of information that's given to you by a z-score is the direction of the difference. So is the score above or below the mean? If the score is above the mean, then it's a positive z value, and it's to the right of the mean in the distribution. So as scores go above the mean, as scores increase above the mean, you're going to see positive z-scores over here, meaning that the scores are above the mean. Conversely, if you are looking at a score that's below the mean, the z-score will be negative, and it would be located to the left of the mean in the distribution. So lower than the mean, in this case, which is 70, all the z-scores over here would be negative. Now, the distance is really just how many standard deviations away from the mean is any given score. And so that is provided by the number for the z-score. So you've got the sign and you've got the actual numeric value of the z-score. The sign tells you the direction, and the number tells you how many standard deviations away that score is from the mean, or the distance from the mean relative to the spread in scores in the distribution. So conceptually, the z formula looks like this. You simply look at the difference between the mean and x in the numerator, so the difference between the mean and the raw score. Then you compare that to the standard difference between the mean and the raw score for the entire distribution. So how different is my score from the mean compared to what is the common difference among scores and the mean, or how spread out are scores? Well, written in symbols in a mathematical formula, it looks like this. So the difference between the score and the mean compared to the standard difference between scores and the mean for the entire distribution of all of the scores. So going back to that picture, looking at the two different distributions, one with a low degree of variability and one with relatively more variability, you can see that when you have more variability in the distribution, your z-scores are also more spread out. Because if you think about it, all right, a z-score of 1 means that you have a score that's 1 standard deviation above the mean. So if the mean is 70, then a z-score of 1 corresponds to a raw score of 70 plus 17, which would be 87, which is roughly here. Going the other direction with the yellow distribution with a mean of 70 and a standard deviation of 17, if you are 1 standard deviation below the mean, z-score of -1, 70 minus 17 is 53, and so your z-score would be right around here. Now compare that to the blue distribution. When you have less variability, scores are more clustered around the mean. They're more, as a trend, scores are closer to the mean. So if you look here, the z-score of 0, right at the mean for both distributions, and that's because a score of 70 is 0 standard deviations away from the mean, because it equals the mean. Same thing going on here. A score of 70 is still 0 standard deviations away from the mean, so the z-score would be 0. But now let's look at 1 standard deviation above the mean, a z-score of 1. Well, 70 plus 1 standard deviation of 10 is 80. So if you had a score of 80 in this distribution, then your z-score would be 1. Whereas over here, 1 standard deviation below the mean, 10 points below 70, z-score of -1, 70 minus 10 is 60. So you can see that when you have more variability in your sample, a larger standard deviation, your z-scores are more spread out because there's more distance in between each z-score, at least each, 1, 2 on either direction, because there's more points separating each z-score. Well, here, there's less spread because the standard deviation is smaller, so getting from a z-score of 1 to 2 is only 10 points, whereas up here, getting from a z-score of 1 to 2 is 17 points. So now let's do some calculations using the z-score formula that I'll write right now. Z equals x minus mu over the standard deviation, or the actual score minus the mean of all the scores divided by the relative spread of all the scores from the mean. Okay, so if x is equal to 70, then z is equal to 70 minus the mean of 70 divided by the standard deviation of 10. Well, that becomes 0 divided by 10, and that is 0. So remember, whenever you have a score that's equal to the mean of all the scores, that z-score for that score will be 0 because it's 0 standard deviations away from the mean. All right, let's try the next one. So when x is equal to 80, what is the z-score in this distribution? Well, it's equal to 80 minus 70 divided by 10. So see, the only thing that's changing when we're using the same distribution with a mean of 70 and a standard deviation of 10 is the value for x. We're still subtracting from 70 in the numerator and dividing by 10 in the denominator. So 80 minus 70 is 10 divided by 10, and it equals 1 for our z-score. So a score of 80 is 1 standard deviation above the mean. And that makes sense because 80 is 10 points above 70, and the standard deviation is 10. 70 plus 10 is 80. The next one, when we have an x of 85. So z equals 85 minus 70 divided by 10. 85 minus 70 is 15. Divide that by 10, and we get 1.5 as our z-score. So it's getting a little more extreme, a little outside of the standard or typical distance of scores from the mean. And it's a positive z-score because 85 is larger than 70. And so if you look at this, you can say, okay, well, 85 is 15 points above the mean of 70. Well, how many tens is that? Or in other words, how many standard deviations is that? It's 1.5. The last one, x equals 65. So z equals 65 minus the mean of 70 divided by 10. So 65 minus 70 is negative 5. Be careful with your negatives. Divided by 10, negative 0.5 is our z-score. So in looking at this, it makes sense that the z-score is negative because 65 is lower than the mean of 70. And if we look at this, 65 minus 70. So it's 5 points lower than the mean. Well, how many tens is that? It's half of a 10, so 0.5. Negative 0.5 is the z-score. So now let's look at the z-scores for the same x values in the other distribution where we had more variability, when we had the standard deviation of 17. So if x is equal to 70, and real quick, I'll just rewrite the z formula up here as a reference. Okay, so when x is equal to 70, we have 70 minus the mean of 70 divided by the standard deviation of 10, and that's 0 divided by 10, and that is still 0. So once again, if you have a score that's equal to the mean, 70 is equal to the mean of 70, then your z-score is going to be 0. Oh, I kind of messed up here. Let's go. This is actually 17. But the answer remains the same. All right, next one. When x is equal to 80. So now we've got 80 minus 70 divided by 17. 80 minus 70 is 10. Divide that by 17 and round to the thousands place, and you get 0.588 for your z-score. And let's just go through all of these. When x equals 85, 85 minus the mean of 70 divided by the standard deviation of 17 gives you, so 85 minus 70 is 15 divided by 17 equals 0.882. So it's got a little bit of a larger z-score than the one above it because the score itself is farther away from the mean. And then the last one, when x is equal to 65, 65 minus 70 divided by the standard deviation of 17. So 65 minus 70, negative 5 divided by 17. And you end up with negative 0.294 for Z. So in looking at this, not only can you see that the absolute value, despite it being negative, is smaller here than it is here because 65 is closer to 70 than 85 is, but this one's negative because 65 is less than 70. Now, if you go back and you compare these, remember, we're looking at the same mean, the same scores. The only thing that's different is the standard deviation for each distribution. Well, in this one, when you had an x value of 80, the z-score was 1. So it's on the high end of all scores. Well, here, the z-score is 0.588. It's lower. It's less extreme. It's within all of the scores. It's almost on the high end, but almost right smack dab in the middle of all those scores that are bunched together. X of 85 in this lower variability distribution give you a z-score of 1.5. It's outside of most of the scores. It doesn't fall within the average spread of scores. But here, it's not even at the edge of where most scores fall. It's still within one standard deviation of the mean. It's still a very common score because the variability is larger. Scores are more spread out. They're not all clustered around the mean. And then finally, if we look at the x of 65 in this lower variability distribution, this had a z-score of negative 0.5. So it's negative because it's below the mean. And, it's still within most scores. And here, yeah, it's still within most scores, but it's even less extreme than it was here because the z-score is smaller. And 65 is still less than 70, just like it was here, so the z-score is negative. So not only is it important for you to know how to calculate z-scores based on x values, but it's also really important that you know how to calculate x values for z-scores. So you need to know how to look at the z-score, the mean and the standard deviation, and figure out what x value does that z-score pertain to. So there's two steps for doing this. The first step is you need to figure out what distance in raw scores corresponds to z standard deviation. So for example, if you know that you're looking for an x value that the z-score for that x value is 2, then you need to say, okay, well, what distance is 2 standard deviations? And the way that you find that is you just take the z-score and you multiply it by the standard deviation. The z tells you how many standard deviations away the score is from the mean, and then the standard deviation tells you what the standard deviation is. So if it's 2 standard deviations away from the mean, you multiply 2 by the standard deviation, and then that tells you how many points in raw scores your score is away from the mean. Then once you get that, you're not finished because you have to combine this with the mean itself. So this will tell you how far away is this mysterious x value from the mean, and then when you add it to the mean, it'll tell you what the score is. So if you have a negative z-score, then this is going to be negative, and when you take a negative and add it to the mean, then you're going to end up with an x value that's smaller than the mean. If you have a positive z-score, then you multiply these together, you get a positive number, and you'll end up with an x value that's larger than the mean. So let's look at how to do that. So we're working with the distribution that has a mean of 70 and a standard deviation of 10, and we need to figure out what is x when you have a z-score of 0, 1, negative 1, and 1.5. So let's go ahead and do some math here. So to find this, we're going to use the x equals z times the standard deviation plus the mean. Okay, so when z is equal to 0, x equals 0 times the standard deviation of 10 plus 70. Well, 0 times 10 is 0 plus 70, and we end up with 70. Now, I could have known this without doing any math whatsoever because, again, anytime that a score is equal to the mean, the z-score is 0. So I should have known right off the get-go that if the z-score is 0, well, then whatever x I'm looking for is equal to the mean, and the mean is 70. All right, the next one. When z equals 1, x equals 1 times the standard deviation of 10 plus the mean of 70. 1 times 10 is 10 plus 70. We know that 80 is our value for x. So, in other words, what value is 1 standard deviation above the mean? Well, 70 plus 1 standard deviation, 70 plus 10 is 80. The next one, when we have a z equal to negative 1. X equals negative 1 times 10 plus 70 equals negative 10 plus 70, which is 60. Well, what x value is 1 standard deviation below the mean of 70? In other words, what score is 10 less than 70? Well, 70 minus 10 is 60. And then the last one, z equals 1.5. So x equals 1.5 times 10 plus 70. So 15 plus 70 equals 85. So that's how you get x values from z-scores when you know the mean and the standard deviation. And in any kind of quiz situation, you'll be given the mean and the standard deviation and the z-scores, and then you'll be asked to find x. So it's important for you to know how to do this so that when we get to standardizing distributions, you'll be using this formula. And then in the next chapter, when we start to talk about finding probabilities of x and finding x based on probability, you'll need to know this formula as well. So now let's look at using z-scores to standardize distributions. So sometimes it's important that you can choose the mean and standard deviation for whatever distribution you're looking at. Maybe you want to choose a mean and standard deviation that's really easy to understand, or maybe you want to avoid negative numbers or make the metric match that of another distribution. For example, let's say that you're looking at IQ test scores, and you don't want anybody to say they have a negative IQ, so you can change the distribution so that it has a mean and standard deviation that will result in no negative numbers. Or maybe you have multiple versions of the same IQ test, and you want to standardize them to match the mean and the standard deviation for the most commonly used IQ test. Well, then you can standardize the scores on the other test to match the mean and standard deviation for the test that you're trying to match it up to. So, concrete example, no matter what version of the IQ test you take, there's different scoring metrics and different distributions. Raw scores are always converted into standardized scores with a mean of 100 and a standard deviation of 15. So no matter which one you take, you're going to be based on a mean of 100 and a standard deviation of 15. So that way it's possible to compare IQ scores from different tests. So this is really the same principle as converting x's to z-scores to see how extreme your score is on a distribution, or in other words, how extreme your score is compared to the rest of the people in that distribution. But this time, you get to choose the mean and the standard deviation. We can set the mean and standard deviation to whatever we decide to set it to. So there's two steps. The first step is you have to convert raw scores into z-scores based on the original metric. So the original distribution they're coming from will calculate the z-score for x. Then you convert that z-score back into an x value using the desired mean and standard deviation for the transformed distribution. So let's say that the original distribution for this IQ test has a mean of 82 and a standard deviation of 6. But we want to transform this distribution so that it has a mean of 100 and a standard deviation of 15, so that we can compare scores on this test to scores from all other IQ tests. So the first step you would want to do is you would want to convert x to z based on the original mean and standard deviation. So x to z based on the original mean and standard deviation, which is mean of 82 and a standard deviation of 6. So to do that, you need to use the z-score formula. So z equals x minus mu divided by standard deviation. Well, the original x value, so what would an original score of 50 become? The original x value is 50 minus the mean of 82 divided by the original standard deviation of 6. So you end up with negative 32 divided by 6, which becomes negative 5.333. So that's a very, very extremely low IQ score on that test. But what we want to see is if we transform this distribution with a mean of 82 and a standard deviation of 6 into a distribution with a mean of 100 and a standard deviation of 15, what would the equivalent to a score of 50 be? So the next step is to take that z-score and turn it into an x value using the new metric with a mean of 100 and a standard deviation of 15. So now we need that x formula, that x equals z times the standard deviation plus the mean. Well, we just found z. It's negative 5.333. Multiply that by our desired standard deviation of 15, and then plus 100. So then that becomes negative 79.995 plus 100, which is 20.005. That is the new x value. So in looking at this, if we converted a score of 50 on this distribution to this distribution, the equivalent score would be a 20.005 on the IQ test. It's still really low, right? This one's pretty low. 50 is pretty low compared to this. And 20 is pretty low compared to the mean of 100. But the important thing to point out is that this is still 5.333 standard deviations below its respective mean. So if we look at this, according to step 1, right, this score of 50 is 5.333 standard deviations below the mean because the z-score is negative 5.33. Well, that should still hold up here. This score of 20 should still be 5.33 standard deviations, or 15s, below 100. So if we look at this, what is the z-score for this x value in this new distribution? And this is just a way to check your work, so I'm going to put it in red. So z equals x minus mu over the standard deviation. So I'm going to plug in my new mean and standard deviation and my new x just to make sure that it's still 5.33 standard deviations below the mean. So this is equal to 20.005 minus 100 divided by 15. And 20 minus 100 is roughly negative 80. Divide that by 15, and we get negative 0.5, or sorry, negative 5.333. So this score is still 5.333 points, or standard deviations, below the mean, just like this one was in the original distribution. So the last thing that I want to talk about is using z-scores for inferential statistics. Now eventually we'll start to calculate z-scores for samples instead of just looking at z-scores for x values, but for now you can make inferences about populations based on z-scores for all the values in your data set. So remember, inferential statistics uses limited information from the sample to answer questions about the population. So it's not usually possible to collect data from an entire population. So if you want to study something like the impact of training on performance, you can study it with a subset of the population or a sample. And the z-score can be used for inferential statistics to see if a sample is representative of the population or if scores in the sample are extreme compared to the original population. So here's an example. You could ask yourself, are the majority of trainees still representative of the population in terms of performance after they received some sort of training? So you have a sample that you take from the population. You assume that they're pretty representative of the population. Then you give them some sort of training. Then you measure their performance again and hope that it is extreme compared to the population who hasn't received training. So another way to ask this, are the majority of trainees no longer representative of the population? If so, then training has an effect. So let's say that you're an HR manager at Netflix and you want to test a new training program designed to decrease overall call times. So this is really a good indicator of performance because the managers want you to have really low call times. So this training is designed to decrease call times. And let's say that before you implement this training to everybody in the company, because it's going to be expensive to do, you want to make sure that it works, you randomly assign 10 people to participate in this new training. After they participate in the training, you collect some data for 2 weeks and observe their call times. And then you want to compare their call times to the average call times among all employees to see if training actually has an impact on performance. So in this example, let's say that among all employees, the average or the mean call time is 8 minutes and the standard deviation is 2. So you can see the z-score formula up here is x, so whatever the call time is for that particular person, minus the overall average mean call times in the entire population, divided by the standard deviation in the population of 2. So let's just look at the frequency distribution table for now. So after training, remember 10 people participated in training, and then we looked to see what their call times were. One trainee had an average call time of 7.5 for the 2 weeks after training. One had an average call time of 6.5. One had an average call time of 6. One of 5. 2, 4.5. 2, 4. 1 for 3.5. And then 1 had an average call time of 3. So in just looking at this data, we can see that everybody who received training actually had a lower call time or shorter call time than the population who had a call time of 8. But this could just be due to chance. You never really know. This could just be a fluke. So it's not enough to just say, oh, well, the scores are lower, so let's go ahead and implement the training. It costs a whole lot of money and may be a waste of time if it doesn't actually work. You want to make sure that the trainees have extremely lower means than the population so that it actually makes you confident that if we implemented this training company-wide, it would probably work on most people. So that's where the z-scores come into play. So if you look at the z-scores, they're all negative, and that's because all of these values are lower than the mean for the population. But if we're just looking at these people right here, this isn't really that impressive. They're still within, most of the call times. But when it starts to get impressive is when you say, okay, well, these people are starting to fall outside of the majority of the distribution. In fact, 2, 3, 4 out of 10 trainees had call times that were 2 standard deviations or more below the mean. And just for now, any z-score that is plus or minus 2 or more, so -2, -3, -2.5, or +2, +4, anything that's with or more than 2 standard deviations from the mean is going to be considered extreme. So these are extreme. So I would say if I was the person that was collecting this data trying to make a decision, I would go ahead and implement that training, because not only does everybody have faster call times, less time on the phone, which is the desired effect, but there's a lot of them that have extremely, extremely less call times or shorter call times. And that's a good thing in this case. That's what we want. So we could be pretty confident that if we gave this training to everybody in the population, it would probably have the desired effect. So that is all that I have for you for z-scores. And just as a summary, z-scores tell you how many raw scores, or how raw scores compare to all the scores in the distribution. The z-scores number tells you how many standard deviations away from the mean is your score. The z-score sign tells you is the score above or below the mean. And then just remember that the z distribution always has a mean of 0 and a standard deviation of 1. Now, the next chapter is taking z-scores and using those to look at probability. So make sure that you're really comfortable with calculating z-scores based on x, the mean and standard deviation, and calculating x based on z, the mean and the standard deviation.